Uh, Hello, everybody. Uh, so I'm Ingvar Stepanyan. I work at Cloudflare as JavaScript performance engineer. And then in reality, I'm more writing like static languages like C, Rust, Go, whatever. In my spare time, as some of you know, I still love JavaScript, even though I'm writing like more static languages at the work. And in spare time, I'm trying to understand JavaScript through compiling it. I worked in different projects like Parsers, Acorn, Experiment, and so on. And as he said, I contributed to Babel and so on. And while parsing was interesting, I believe that you can truly understand the language only when you try to actually understand how compilers work, how they optimize it, how exactly, like what is good about it, what can't be optimized, and so on. So I'm going to talk about how I spent my summer or tried to compile JavaScript. I'm trying to, basically in my spare time, trying to build a static optimizer / compiler for JavaScript in Rust. And I like to walk you through through the stages that we need to go to build one. So generic compilers pipeline looks something like this. We have different languages. They go to front end, phase, middle end, back end, and then from back end you get CPU code, CPU-specific code. All the languages were one-phased. For example, Pascal was designed specifically to be able to compile it in only one phase, but it's not very easy to perform different optimizations on syntactic level, so it's easy to split it into different stages. And I just really like this picture from Wikipedia, because it could be easily adapted for this conference. Thanks, Java, for the name. So I'm going to use it through entire talk. So yeah, it doesn't matter really if you are compiling C, C++, other JavaScript, or anything else, because generic optimization techniques are pretty much the same, and generic ways of doing it are also the same. The only difference between JIT and static compiler is that JIT can get more information during the runtime and use it for the same optimizations that static compiler can analyze only through types. So first of all, you get your actual source. Let's take one that everyone has probably seen in the interviews. You get some text. Let's take a small part of it. What it is for the compiler initially is just a string, like very dumb string, which is basically just an array, just an array of characters that you need to do something about. It's not really meaningful or anything that you can work with. So first thing that you need to do is actually split it into meaningful pieces. And the tool or the part of the tool that does this is called the lexer. Lexer just processes the strings from the left to the right by going through characters. What it does is basically recognizes sequences of characters that are in its dictionary. If it doesn't recognize some, it's early syntax error. If it does, it just marks it as some group. So for example, it knows that sequence of letters that contains VAR is just a keyword. It goes next. It sees like the white space, which is really meaningless in the grammar. It can skip it. Then sequence of letters that is not in the keyword list. So it's just an identifier. Then this again like meaningless white space. Then this equal sign. Equal sign is just a punctuator, another meaningless white space. And then this like digit 1, which in JavaScript grammar is defined as just a number. So it recognizes it like this. So out of array of just meaningless characters, you already have some groups that you can work with even in streaming mode if you wish. Now, out of this array, you get like basic tokens. You can do some things like syntax highlighting or very basic syntax errors checking and so on. But it doesn't really give you anything close to original program structure. So the next part that comes after the lexer is called actual parser, which takes this stream or array of tokens and transforms it into a structured representation tree that looks like your source as when you read it. So what it does is, first of all, it tries to parse a statement. It knows that statement that begins with var is variable declaration. Right? Then variable declaration, think of it as just a simple recursive function that calls other functions. Each stage is just another function that is called recursively. So variable declaration just knows that it needs, after the keyword was matched, it needs to parse identifier. So it tries to match the, it needs to parse variable declarator. Right? Variable declarator is actual assignments in this var list. You can have lots of them. In this case, we just have one. Then variable declarator knows that it needs to parse identifier. Then it expects equal sign, it finds it, no syntax error here. And then it expects some expression. This expression, in our case, just matches this number. So now you get some tree, like not to make slides too verbose, I'm not posting JSON object here, how it looks like, but it gives you complete structure of your program just as you would read it. Like, you know what exactly lies where, you can actually analyze it and so on. So for simplicity, we will just represent it as original code. But you can think about it as also a structured way. So what you can do about it? Turns out, like, not so much. It gives you complete syntax representation that exactly follows what you have in your code. It gives you a complete structure and so on. What you can do is like basic linting. You can do what Bible does, just transform one syntax into another. But you can't really perform lots of optimizations on such form. The reason for this is it actually is exact representation of your code. And it's very verbose. So for example, this is the same code that you have with for statement. You could just write as well with by moving I to the top and writing while loop. Or you could write it using do while. All these representations will look different in object form. For each of them, you would need to write a handler that processes specifically this case, that optimizes specifically it. It's not really helpful to have this. So that's exactly why middle end exists. We transform this high-level representation with different syntactic forms to less of them. So let's take a look again at our example. To transform from front-end to middle end, we need, first of all, to remove all the JavaScript magic. First of all, there is this sweet scoping, where we can hoist variables, functions, and everything we need to actually know about them even before they were defined. So what we need to do is actually move them out to the top. After that, everything else remains just as simple assignments. The next thing we need to do is unwrap any syntax sugar. So for example, I++ is just I equals I plus 1, right? Result multiplied by I is just result equals result multiplied by I. We already have much less syntactic forms that we need to care about in such form. Next thing that we need to do is let's transform all the loops to just one single form. Let it be while in our example. So at this point, our program is still just the same JavaScript as it was before, but we have much less nodes. We don't have all the other types of loops. We don't have all these combined assignments with binary expressions. And we can omit all the scopes because like all the variables are already collected. All that we need to do is just assign them to some initial value, which in JavaScript is undefined. We try to be as explicit as possible and actually assign them result equals undefined, I equals undefined. I'm omitting the variable declaration because now we can assume that every variable was declared already. We collected it. Next thing we need to do is very interesting. Like, we have this tree structure, but still, like, it's not very easy to work with trees recursively for any kinds of optimization. What we really want to do is have a notion of how your program executes, from where it goes to where, in which order, like where it can jump and so on. So you want to split it into separate blocks that jump to each another. And here we get our favorite go-to that everyone told us not to use. But turns out it's exactly what computers use underneath for any of your fancy loops or switches or ifs or whatever. So now we have separate blocks, and each block is just a flat list of statements. It's as simple as possible. And each block ends with just either direct go to another block or conditional one. So we see that initially we set all the variables, then we go to another block that just checks condition. If condition is true, it goes inside of the loop. If not, it goes back. It goes directly to return a result. Then loop itself just executes its internal body, goes back to the condition, and so on. So here we have just flat list of statements in each block, and they are interconnected between each other in the way the program executes. One optimization we can already do, and most compilers really do, is it's not really nice to have this condition in separate small block, because we could better optimize it if it would be spread separately in block 1, where it's executed just once, and separately inside of the loop, so that we wouldn't need to jump forth and back every time from inside of the loop body. So we just inline it. So in block 1, we now have this condition, temporary variable, that is being checked. Then it goes to block 2, and block 2 just goes into itself every time the condition is evaluated true internally. Are there any questions so far? Looking at your faces, I guess says a lot. Okay, now we have direct execution order. But one thing that still doesn't help us is that every variable can be reassigned to anything else. And we don't really know where the value comes from. We can't constantly evaluate them. We don't really know the origin of each variable. We just know that it's somewhere. So the idea that compilers use, all the modern compilers use basically, is immutability. Just the same immutability that you use in React with just the same benefits. So basically at each stage, you just have separate state of variable. And each variable is assigned exactly once, and you can do time travel debugging, you can figure out where it came from, and so on. So let's just index each variable with its position so that all the variables in our code would be unique. So now we have this R1, which is undefined, R2, which is 1, and so on, and so on. So in the first block, it was easy. The block 2 and block 3 are somewhat more complicated, because just if it's not clear, at each point we just use, instead of variable, the last variable that lived to this point. So for example, if we had I, we use I2 because it's the last one that was before the condition. Make sense? Cool. In block 2, it's slightly more complicated because we don't know exactly where R and I come from. They can come from either block 1 or come just from inside of the loop itself. So there's special instructions that marks these kinds of variables. Engineers at IBM, when invented it, just called it phi. And phi basically just chooses, depending on which block we came from, chooses which variable to use. So if you came from block 1, we use I2. If you came from block 2, we use I4, and so on. Now, what are the benefits of such approach? As I said, we know exactly where each value came from. And why is this important is that we can immediately see which values are not used at all. And that means that any assignments to these variables can be just safely dropped. So now we know that undefined is obviously not used anywhere, R1 and I1, we just drop them. Is this clear? Now, we see that I2 is always a constant. We can directly inline I2 to its usages. So cond1 is now just 2 less than or equal than n that we got as an input to our function. And phi also uses now constants directly. At this point, we can't really do anything about this function as itself, but what we can do, if this function is called from somewhere with constant value, then these blocks are inlined. And we know immediately that n1, for example, if it was called factorial from 1, we know that n1 is 1. And in that specific place where we called it, we can inline this function and optimize it further. So now we know that n1 was 1. We can replace all its usages with this constant value. We see the condition is now just 2 less than or equal 1. We know that its just never executed. So we can completely evaluate it to false and just completely drop the block where it never goes. And from this block, it becomes obvious that we can just drop goto completely. So in that specific place where you call your function with some constant value, compiler will be able to just optimize everything away and figure out the constant value immediately and inline it. Let's take a look at some more complex example. What if it was called with 10? Then our condition is immediately true. We just drop the jump, but not the block. Now we know that we go immediately to block 2. And now optimizer can see that when we come to block 2 from block 1, it starts with just constant values. And everything else in the block is just evaluated out of those variables. Like there's no other input. So what it can do is just derive from those constants all the other variables, go through the loop, everything at compile time, and evaluate R4 immediately. So even if it's more complex, optimizers this way, using just immutable variables, will be able to calculate the value of your factorial function inlined elsewhere, or any other function. Afterward, you can obviously just immediately insert the final value into your code. This is actually all possible and what JITs do. Okay, I'm going too fast through this. I was too sleepy. So the next step is when we go from this middle-end representation to backend. Let's get back to our original example. Or rather take a simpler one, because this one's already overcomplicated. We just have sum of x and y, which returns x plus y. It looks so simple, and like what we can do about it, yeah, it's just block which says result equals x plus y. The problem is that any real CPU is not dynamically typed, unlike JavaScript. It needs exact types at each point, and it needs to know what exactly is x, what exactly is y, and what the hell operation plus means on them. In JavaScript, it's not so obvious because plus can mean concatenation if any of these values is string. It can mean addition of actual numbers if they are numbers. Or if one of them is objects, then everything gets even more complicated and you need to call .value off and evaluate the number and inline it and so on. How can we represent dynamic values in statically compiled languages as ones that we try to target? One common approach is basically just having a structure of two fields, which has type separately and value. So type, we just tag some number, which we assign to each specific type of JavaScript, basically booleans, numbers, undefined, null, whatever. And we can define our operations through runtime functions. This is where things get interesting, if I can say so about this. So we can define every operation through just function that is later linked with our compiled JavaScript. And every time you call this operator, it will be calling that external runtime function, which will be checking types and returning result dependent on them. This kind of functions is it really helps us with building quick prototype of language. But the problem with them is that they're not really inlineable. Optimizer can't know anything about them. You end up with lots of calls. So for example, if you try to just do the same operation add on with even constant value, optimizer can't know that it needs to just add 1, not to go through type checking for the second value y and perform all the other operations. And when we tried some more complex examples, things become even more complicated. We actually need to define function for every single operation. Like if we try to just calculate distance between 2 points, we would need to define separate runtime functions for subtraction, for multiplication, for addition, square root, like everything, basically everything that we have in JavaScript. This is not only verbose, but also not very helpful when trying to optimize it. So what can we do better about this? One thing that we know is that subtraction, for example, always works only on numbers, right? There is no way it will, if it tries to work on strings or anything else, we just transform it to number and perform subtraction. Same can be said about multiplication or square roots. So what we can do is, instead of using separate runtime functions for each of our operations, we convert numbers just once. We have separate operations that just converts value to number, and then we just execute native processor level subtraction. Same for div2, and for multiplication, we already know that result of subtraction is always a number. We don't need to call any runtime function. And for sum, we also know that all these multiplications also return numbers. So everything becomes much more simpler because we don't need all these runtime functions anymore. Instead, we can just directly use all the native operations that are available on your CPU. And actually, this works. This is how right now mathematical parts of your JavaScript can be compiled statically and rather linked with C or whatever else. And the final part is where backend is transformed to CPU level instructions. Well, at this point, what we have just lots of variables, all the temporary variables, which don't really fit into CPU registers. On most CPUs, you have, like, say, 16 registers. And programmers tend to use variables as if they have infinite numbers of them. After all the transformations with immutable variables, we have millions of them all throughout the code. So at this point, backend needs to transform all the variables into separate pieces where it can actually put them into those registers, use them, and then free them for other variables, and so on. To be short, I'll explain just like magic. I'm not going through all of this. And basically here we could end. I would really like to discuss a few other pieces. I mean, we got to the last stage where it's converted to CPU. It's done by magic compiler. At this point, I would like to discuss a few other things that are tricky to transform even at the front-end stage from syntactic level to the medium one. But I'm not sure if you want it. OK, so let's just leave it either for questions, or I can just go through some other problems that we experience when writing compilers.
I think it also worth some applaudissements.
Hi. So when we translating code from medium phase to backend, yeah, we generate a lot of compiler generates a lot of functions for different types. So if you take some function, for example, I want to call it one time with numbers and second time with strings. How a compiler, it's not compiler, interpreter will differentiate these cases, and if, for example, I called this function a lot of times with numbers, yeah, just-in-time compiler kicked in and compiled a native code for this, and then I passed string to it.
Well, you see, the idea is that we pass, every time we pass a variable to this runtime function, we actually pass a structure of both type and so, whatever. 1 second. I'll just show it. No, it's not helpful. I just want to see it too. Yeah, this is code of my compiler, don't look. So the idea is like when on JS side you have this sum of A, B. And you do this return runtime add AB, yeah? This runtime function actually accepts basically, let's imagine that it's also written in JavaScript for some weird reason. Runtime add, this invalid syntax code KS. So basically it has this type value and type value. And what middle end does, it transforms also A to basically type of value, and actual value just bitcast it. Same for other one. And here runtime just goes through all the combinations of types and returns a result depending on it. So basically, if type is strings, and it returns concatenation to that place, and so on and so on. So it also returns the structure of type value. Then you get these boxed values all around the code. But yeah, I told like what the problem is with that and why it's better to unbox it exactly at compile time. Yeah.
Okay, thank you.
Thank you for your presentation. It was awesome. And can you hear me? Hello? If I understand you right, that developers, JS, in this case, JS developers could write code that that will be easier and faster to machines to understand it, right?
Yes.
And run.
Ideally, you should write code that is easier for humans to understand, but yeah,
so
you can do that.
I understand you right, thank you. And then my question is, there should be some kind of balance between that human should understand this code and the machine should understand it and work faster. What do you think about this?
Well,
because if we always will be declare everything at the top and so on. It's
yeah, like I'm not sure if actually V8 or anything else does that about like because it can't really know if you reference variable whether it's defined further down the function still or not. If you could somehow hint it that like there is no other. So what I mean, like, well, let's just continue. This is fun. Whatever. So you have X, Y, and so on, and
you have equal define, for example. Equal define.
What?
Equal undefined. I'm sorry. No.
Yeah. No, I mean equal undefined is not really necessary because like that's an easy part for compiler. What's hard for compiler is, for example, if you try to call G from this X, Y. Like, is this G just some global function here? Or maybe it's just defined somewhere here. Like that's what compiler can't know when it just parses code in streaming mode. Unfortunately, you can't hint it. So if you try to hoist everything to the top, yes, it will immediately be able to resolve this. If that's your question.
Yeah, thank you.
Another thing that you can do to hint compilers, for example, like as we said, like unboxing numbers, it's immediately obvious for other operations. Like if we got a number, then we just do, for example, simple addition and not try concatenation and so on. So what you can do, basically simplified form of ASM.js, where you at the top just do, for example, such weird things, which basically convert every argument to integer. And then starting from this point, compiler will know, okay, it's in integer, I can just immediately emit integer operations on it and not try all this with types and boxing and so on. Yeah.
Yes, thank you very much. I think this such kind of hints are very useful and would be nice to saw them more.
Yeah, so what I'm trying to do actually with this compiler is that the talk derived from is to give ability to just write normal functions which get optimized and compiled to LLVM, and then LLVM acts as middle end and backend compiler. So we get to the stage where we have these boxed values and pure numbers. Then LLVM basically compiles this everything, like optimizes what it can statically. And then from LLVM using mscript, and you can, for example, compile it back to ASM.js or WebAssembly or whatever. So basically, it will have these hints included already and all the possible pieces of your code optimized out.
Hello, thank you for your speech. Can you please explain how does compiler define type of objects? Because it's difficult. The objects could be with dynamic properties, and how the compiler action with them in runtime.
Ah, you mean the like real objects?
Yeah.
Well, there are several approaches to this. So the very basic thing you can do, and that LLVM even will be able to help you with, like any static compiler, is when you define every object as just opaque type, so basically just void star. I don't know if I should write C syntax in JavaScript conference, but so you have void star, say obj, let's say it's just runtime create object, and say you just define every property by also using this undefined runtime functions. So say runtime get property, and we dereference it and set, for example, to 1, get property, say x. Then in other place, we do local, like runtime get property. So even though those runtime functions might be completely like not defined anywhere, you might not even be able to link with them, you can still put those attributes if you saw them in the presentation. So basically, read none, for example, it's valid LLVM attribute that tells LLVM that this function never tries to read memory anywhere else. So what it means basically is that this function is constant, and yeah, I should probably pass object. So that this function is constant, and like it uses only arguments and not some global state anywhere else. So what can what I'm doing? So what can optimize the figure out even from this is that, like, okay, if it's constant, then apparently what I assigned here can be just directly used here. So at the very least, it will be able to optimize this thing to like just 1. That's one approach, as I said, to work with this. Another approach is what JITs do is basically like if your object doesn't change over time, if you just constructed it and it's that way, then just creates immediately local structure, basically native structure with all these fields that you have in your object inlined, one after another. And it assumes that it will be always like this. If you break that assumption, then it goes back to this map mode that I showed here. That's a short version of it, yeah.
Okay, and when we are creating object in this way, why you avoid asterisks, and then we should allocate some memory, and does this memory is some static number of bytes, and then we increase it or allocate it? How it's optimized?
So for now, if you want just to optimize it and then compile back to JavaScript, say ASM.js or whatever, you don't really care about the implementation. So we can assume that create object is the one that allocates memory somewhere. Like, in fact, for example, LLVM actually supports also intrinsics. It has own like runtime functions, something like LLVM GC initialize and so on and so on. So you can tell it that, okay, this should be allocated with a garbage collector, which I'll like link it somewhere else later. But that's only useful if you want to actually compile it to native code with that garbage collector and run it as native application. Like, it's not as useful if you want to just optimize it and compile back.
And what do you think about when we have some libraries, for example, written in C or C++, and we compile it to JavaScript? Why they're so big, and it's compiled by LLVM, but they are so big, and you just show us some little pieces of this. Why they're so big? Do you know?
Sorry, what is big?
When we have some libraries written in C, we can compile them using LLVM into JavaScript and use it in our browser.
Mhm.
And
So you're using mscript then for that?
what?
You're using mscript then for that?
No. I compiled the C++ program into JavaScript, and I was surprised why they are so big and have more.
No, I understand that. Like, what are you compiling it with from C++ to JavaScript?
For example, library for converting image to some.
No, compiler that you are using. What is that?
LLVM.
I'm sorry. I'm sorry for interruption. We're limited in time, and I think that this discussion, well, could be continued after the talk because.
Okay, so to be short, C++ is just bad. Like it generates lots of virtual tables and so on that need to be compiled to JavaScript. Just use JavaScript. Yeah.
Yeah, I totally agree.
Oh my God, people actually asking questions.
Hi. My question is kind of instead of previous questions. So we know that most of the languages on your very first slide are static type languages. C, C++, Java, but JavaScript is not. And I have two questions. How much more complicated is compiler because of dynamic typing? And how much of the performance we lose because of not statically typed JavaScript? What do you have some estimations?
That's exactly what I tried to cover in the last sections where we go like for dynamic types.
Yeah, I mean, obviously it involves some more complicated compiler, I expect,
No.
to compile it.
So you mean statically or as a JIT?
I'm not sure I get your questions.
So like basically you mean like how it's done currently in browsers on Node.js, or if you want to do that statically? To actual .exe that you can run somewhere else.
I'm interested in actually in both cases because as from my current point of view, I am not sure if it's really different penalty in terms of performance or complications. Is it different? It would be interesting to know.
Well, it's different in this because we need to represent every value as this type and value structure, like basically a box for that value.
But in runtime, we also need the same thing.
Yes,
we?
but like if it's optimized the way, for example, if you are using just numbers and you actually give those hints that we just discussed, like
yeah, I understand.
You can unbox it and then it becomes just pure native code, just like any other that works on numbers.
Yeah, but
so we don't lose anything on that point.
If I write special code like SMJS, I understand that I might get this similar performance, but I mean, for
no,
typical
even
code,
without SMJS, you can actually get that totally.
If I don't put the hints, if I write usual code.
Yes, like if you write usual code, you can still just write code in the way that will help compiler.
No, it's not usual. If I write in specific case, it's not usual. Open like React.js, any JS library. It's not written in that style. So
what is your question?
How much?
Sorry.
How much performance do I lose because of that?
I think it also. Well, I'm not following the question. I think Ingvar also, and maybe you should continue also with some private discussion because a lot of people don't following the question. Okay, it's really strange to continue with questions from such interruption, but guys, do you have questions which you consider are interesting for other people maybe? So it's not a conversation in the audience of 200 plus people, right? It's a kind of highlight of your thoughts. And any?
There is one, apparently.
Thank you for your presentation again, and I have a question about console.log. What should be behavior of compiler if I, for example...
Sorry, I missed question about what?
Logging to console.
Uh-huh.
What behavior of compile I should expect if I place console.log, for for example, in first function with factorial, should compiler do something with this function or not?
No, it can't really do anything about it. I mean, after inlining, it will optimize away all the all the variables that it can actually see that come just from constants, but console.log is just third-party function that is not available in local scope, so it can't know how to optimize it, should just leave it, yeah.
Thank you.
Ideally.
There was some question.
Can you tell us some certain examples of area where you apply low-level techniques to optimize something? Some practical examples where it is very useful or some...
Very useful for whom exactly?
Again, please.
Very useful for whom?
For your job, for your...
Ah, okay. I mean, I don't know why I'm talking about this, because I doubt it will be useful for most of JavaScript developers. I mean, apart from knowing how to actually tell compiler that, like, okay, I just want these numbers and so on. Like, basically help compiler optimize something. And second, as I said, like, it just helps to understand language if you know how exactly it optimizes at low level. So you know what is going on. For me, it's interesting because I really like JavaScript. And I'm writing C, and I want to build a compiler where I would be able to still write JavaScript, but compile to native code that we can put anywhere and basically behave it exactly as C. So the difference would be just syntax and type rules and so on. So this is basically why it's interesting for me. Because on Cloudflare servers, we obviously can't put entire Node.js to process millions of requests per second, while if doing some static optimizations before that and compiling it to native code, it could be theoretically possible. That's why this area interests me, and I'm playing with it.